Hello everyone, Assalamu alaikum. Welcome back. In this video, we are going to talk about automatic differentiation. In order to understand automatic differentiation, I think it's helpful to take a look at computational graphs. So, computation graphs are a graph of computation or calculation that we define or execute in PyTorch. In PyTorch, in particular, when we implement neural network models, there will be two methods. One is the forward method and one is backward method. So in the forward method, it constructs the graph, and then the backward essentially computes gradients by walking backwards. So forward graph is constructing a graph. If we have a graph with multiple inputs, some computations, this is the forward method, and then the backward method, based on the output, we compute the derivatives of the output or loss with respect to these inputs. For example, the weights that we want to update. So in this video, I want to briefly go over what such a computation graph is and how we work with it conceptually before we see how PyTorch handles it. In the context of deep learning and PyTorch, it is helpful to think about neural networks as computation graphs because neural networks are really just a chain of computations like nested computations. Now let's take a look at an activation function that is not a linear activation function that we have studied before. So if you recall the Adeline model, what we had was a computation that computed the net input, which was then passed on to a threshold function. So the net input is considered one weight, one feature was computed as follows. And then we had in Adeline this activation function, which is just an identity function. And now we are taking a look at a function where the sigma is not an identity function. So we are now taking a look at this ReLU function. This ReLU function is in the context of a neural network usually takes also the net input, and we will revisit this ReLU function also in later videos and also talk about why it is so commonly used in deep learning. And for right now, just think of it as an activation function that is almost like a linear function, but not quite. So the shape of this function is as follows. In the plot, I'm showing you how it looks like for different inputs. So here we have input to the function, for example, the net input z. And here we have the output on the y-axis. And the ReLU function is defined as almost like the identity function. So it returns z, the input, if z is greater than 0 and 0 otherwise. So it really is this region and identity function. And here it's not doing anything on the left hand side, so it's clipped. You can think of it as a clipping. So why is that useful in the context of deep learning? We will talk about this more, but this is essentially yet to have a non-linearity in the multi-layer network, because if we have multiple linear functions, regular linear functions, the combination of linear functions is also a linear function. So in a sense, our network won't be able to approximate non-linear functions, but that would be going a little bit too far ahead. We will talk about this more in detail later on. Here we just care about the computation. So also note for this ReLU function, this one would be not differentiable in a mathematical sense. This is a function that is not differentiable. So in this case, we have a derivative of 0. If input is smaller than 0, the derivative of one of the input is larger than 0. But otherwise, if input is exactly 0, then the derivative does not exist. So what do we do now? Oh, in computer science or in the computational context, we are not that picky. We just make a small adjustment. So we adjust the derivatives as follows: that it is 0 if z is smaller or equal to 0. So that's just adding this smaller equal to here to fix this issue. And otherwise it's 1 if z is greater than 0. So it's so rare that we hit exactly 0 anyways, that this will probably never happen in practice anyways, because usually we work with floating point numbers like lots of digits of decimal points, so it's very rare to hit an exact 0. So even though it's not differentiable in a mathematical sense, we make in the computational case this little adjustment and define the derivatives as follows. Now let's move on to the computation graph. Now just to summarize, now we have the following activation function. This is just a summary. It's a multivariable function where we have three inputs. We have the features. So here we only have one feature for simplicity, one feature, one training example for simplicity. We have the bias unit and the weight parameter. Also for simplicity, only one weight parameter corresponding to one training example feature. So as you recall, we usually calculate the net input, for example, in Adeline, and then we would pass it to an activation function. In this case, we use this ReLU function. Right now, we don't have to think about the networks. If you don't want to here, you can just think of it as a simple computation that we want to represent using a computational graph. So how would we do that? Let's see. So here would be a computation graph of this function. I use some intermediate variables to make this a little bit easier to read. So we define this computation as u and we define this computation as v. So we have three inputs, like I said, input 1, the bias input, um, the input 2, the feature, and the input 3, the weight. What we do is the first part, uh, here we compute u. So this is multiplying x and w. So this is just multiplication here. So we define u as a placeholder and u is equal to w times x. And then what we do is we add the bias unit here. So we have u plus b. So we have this operation here which gives us another variable v. And then v goes through this activation function. In the context of deep learning, we are usually interested in computing the partial derivative of the loss function with respect to the weights or bias unit, as we have seen in the Adeline, and we can actually decompose that into smaller substeps. Using the chain rule, we can also decompose it into the partial derivative of the loss with respect to the activation and times the derivative of activation with respect to the weights, and so decomposing it. So here we have a simpler computation graph. I haven't included a loss function here. What we are actually looking at here is only the activation. So we are in this example only walking through this part. So the partial derivative of the activation with respect to the weights, which we can also further decompose into substeps using the chain rule. So that's what I'm doing here. But that's what I'm going to show you in the next couple of slides. Here I have the first step, so computing the derivative of the activation with respect to the input of the activation. Here this is the term of the derivation of a with respect to v. That's the first step, and using this computation graph we can really make this super easy. So the next step would be, for example, computing the derivative of v with respect to b. So because we are interested also in the bias, because bias is also like the weight and model parameter. So the next step is computing the partial derivative of v with respect to b. And then we can do this also for the other parts. So what's so nice about this computation graph is that we can do it step by step. We can for each computation do a backtrack here and annotate our graph. And then we can put everything together. So if we are interested in the derivation of a of the output with respect to the input, we just need to use the chain rule. So we can then write this as derivative of a with respect to v times v with respect to b. And we can also do this here at the bottom, right? So this is what I've done here. If you want to step through that in the slides. So I was just putting things together here. Let's now take a look at concrete example with some actual numbers. So assume the base unit is 1, the weights are 2, and we have an input of 3. So the intermediate value u would be then 6, right? Because 2 times 3 equals 6. And then 6 plus 1 is 7. And for the ReLU function, because it's positive, it's an identity function, so it's also 7. Now let's differentiate. So the derivative of ReLU function, if the input is greater than 0, is 1, right? Because it's an identity function. So the derivative of this part here would be 1. Then let's compute the derivative of previous steps. So if we look at v, so v, you can think of it as a sum of two functions here. So the derivatives can then be computed separately. So if you look at, let's say the upper part here, the derivative of v with respect to b. So in this case, u is a constant, so we can ignore that, and the derivative of b would be 1. So there should be a 1. And similarly, the other way around at the bottom here, b becomes a constant, and the derivative of v with respect to u is then also 1, right? So we can also put a 1 here. Now moving on, so we have a derivative here. What do we have here? So this is just w times x. If we compute the derivative of u with respect to w, then the derivative would be x, and x is 3. So here we should have a 3. And then putting everything together, the partial derivative of activation with respect to w would be 3 times 1 is equal to 3, because we are combining with a chain rule. And similarly, we can combine on the results of this part here too. So in this way, the result here would be also yet 1, because it's 1 times 1. Alright, so this is how we use computation graphs, and I will show you in the next video how we can implement this in PyTorch as well, where it computes these derivatives for us. Of course, this example is a trivial one. It's a very simple one. That's something you can do in a few seconds by hand. But if you rethink of the computational graphs as neural networks that are more complicated with many layers and on lots of input features and stuff, it would be tedious to code it up in PyTorch by yourself or in a NumPy. So that is why there's this automatic differentiation that I will show you in PyTorch, which it will construct this graph here under the hood. Like we can actually print out the graph, but we don't have to have it here. It will do it automatically for us. Just some more computational graphs that will be relevant or that are kind of related to deep learning. Let's explore these as well. So here we have an example of a graph with a single path. So you can maybe think of it as a simple adeline or logistic regression model. So this would be the full graph based on what I have shown you earlier. So in the previous slide, I showed you only this part. Now also think of output where we compute the loss, for example, in adeline mean squared error between the prediction or the output and the actual class label. So if we have a case like that, then we can compute the derivative of the loss with respect to the weights. And this can be decomposed into loss with respect to the output. So this would be this part here, and the output with respect to the activation. So this would be this part. And then the activation with respect to the weights, this would be this part. And this is what we had in the last slide as an example. So this would be a simple case of graph with a single path. Now in practice, there will be more complicated constructs. For example, imagine a graph with weight sharing. It is kind of related to what's going on in convolutional networks. That will be something that will be covered later. Here's a simple example. Imagine we have a case, we have a single input, and then we have the weight parameter that is shared. So that's the same weight that goes here to compute some activation. So these could be different functions. A1 and A2 could be on different functions, and that and then we can compute some output. And then also here the loss, like on the previous slide, if we have a case like that, we have to use the multivariable chain rule, because there are now two paths, like there's some weight sharing going on. If we want to update w, it depends really on this path here and this path, right? So we have to combine them. So we have the multivariable chain rule, we compute the loss. So that could be a case where we have weight sharing. And here would be an example of a multi-layer perceptron, which we will be covering in the coming videos. So here we also have multiple paths if we want to update certain weights. So this is a multi-layer perceptron with two hidden layers. You can see there are now two levels of activations. One level is here and one level is here. So this is the first hidden layer, and this is this second hidden layer. And again, this part is like the same as in the previous slide, the loss. Let's say we are interested here in computing the derivative of loss with respect to this weight here, W11, in the first hidden layer. So in order to do that, we compute the loss. Compute the loss, but then also the derivative of loss with respect to the output, that would be this part here. And then we go here, this would be this part. And then we go here, which would be this part. So we are skipping across some parts. We'll do this step by step in more detail later as well. And then we have this part, which is the derivative of this activation, and a1 with respect to this weight. So we are computing with respect to 1 here. However, note that there is a second part, right? So it's again the same. Line 1 is like this one, but we now also have the second path. So we go from output across the second path to this to same weight, but now taking another path, starting with a loss with respect to the output, then output with respect to second activation, and then activation, this second activation with respect to the first activation, and then towards W11. So in that case, you can actually see that things become quite complicated if we have a multi-layer network. And now imagine coding this by hand, like computing derivatives, implementing them in code. It's very error prone. It's important to, on the big picture, you understand what's going on, but you're implementing this by hand, and this is only for one way. It would be very error prone, which is why we actually use deep learning frameworks that can do this automatically for us. So in deep learning frameworks, we only have to provide the forward computation, and then the backward computation is derived automatically, because you can implement simple rules to do that automatically. You just have to be careful implementing these rules once, and then you can always apply them to any arbitrary computations. Okay, so in the next video, I will show you how we can do this automatic differentiation in PyTorch. I hope this was helpful and informative. If you have any comments, drop them in the comment box. See you in the next video.